Hi guys, today I'm going to talk to you about the work done in my degree thesis that is focused on the development and implementation of a network scan detection system based on domain name system, so DNS. So by analyzing DNS traffic, this system can identify suspicious activities such as network scans, which may indicate attempts of network attacks or exploitation or, yes, exploration by malicious actors. So let's look at the structure of my work and the results that I have obtained. To demonstrate the practicality of the proposed DNS-based detection method, I set up a test environment with a small network configuration using the address range 192.168.100.0/24 and 3 virtual machines, each with a specific role, as you can see in this slide. So the first machine is the banning client that generates legitimate traffic by automating web browsing through a Python script. Then there is the scanner machine, so VM2, which performs network scans on external IP addresses using the Nmap tool. And then finally there is the VM3, so the scan detection system, that is the core of the whole experiment, monitoring DNS traffic and detecting scanning activities by blocking suspicious connections. And these 3 virtual machines all resides within the same subnet, and I specifically configured the kernel IP routing table for both banning client and the scanner machine, so that all traffic they generate can be directed to the scan detection system, which obviously acts as the default gateway in this setup, in this experiment. So this is the configuration, the network configuration of banning client, and I want you to show, this is VM1. Okay, so this is the network configuration of VM1, so the banning client with this IP, and while this is VM2 with its network configuration with this IP. And I want you to show also the output of this command that shows the kernel IP routing table. As you can see here, the default gateway is this IP address, that is the IP address of the scan detection system. Okay, so returning to the slide. In this slide, I've included the nmap command that I choose and used during the experiment. This command was executed against a list of remote IP addresses that were previously resolved from domains linked to deliberately vulnerable web applications, allowing for ethical hacking. So this machine wants to simulate the behavior of a network scanner or a network worm that uses a technique called random block scanning. In fact, scanners and network worms are usually engaged in scanning IP blocks. That is a technique whereby they send a probe or exploit the data packets to a range of randomly selected IP addresses within the target network space without a prior DNS lookups. Then there is the scan detection system, so which is equipped with 2 interfaces. So the first, like VM1 and VM2, is set to internal network, so connecting it to the virtual internal network, while the second one is set to bridge the adapter, allowing it to connect to the physical network and the internet. This machine runs a Python script that monitors DNS activities, including DNS queries and DNS response, which are tracked and stored in a hash table that I implemented in Python as a dictionary, and that I named DNS expiration table. This table uses as key the source IP address, like for example, the banning client IP, initiating the DNS query towards a destination, like for example, let's take google.com, concatenated with the destination IP address extracted from the resource record of the DNS response. So in this example, I've just made Google's IP address, where the table's value store the expiration of each of these DNS records. So the system specifically focuses on DNS responses, extracting their resource record and considering both IPv4, or AAAA, so IPv6 records, which contain the IP address, obviously, resolved from the domain name contacted in the DNS query. So following the algorithm that I will explain shortly and that I will show you in the next slides, the scan detection system modifies particularly the TTL values and logs or block incoming and outgoing connections, and then identifying those without a prior valid DNS lookup as malicious scan. So you can easily understand that the banning client, so VM1, who performs normal activities like browsing, will not be marked as a malicious scanner, since it does prior DNS lookups towards the destination, while VM2, so the scanner machine, does scanning activities against target IPs, directly contacting them without a prior DNS lookup. Moreover, the scan detection system can also reduce the TTL value, and this is crucial because if a machine still holds an unexpired DNS record for an IP address, a scanner operating from that machine that maybe was compromised could target the IP without being detected by the scan detection system. This is because the scanner would be using the cached DNS record, since the compromised machine had performed a DNS lookup previously and stored the DNS records, thus avoiding any DNS lookup that might be monitored by the scan detection system. So by shortening the duration of which DNS records are cached, it is possible to minimize the likelihood of a scanner utilizing these entries to perform scans on the IP addresses stored in the cache. And for this experiment, I choose to set the TTL of DNS responses to 300 seconds, so exactly 5 minutes, ensuring that DNS cache entries are frequently updated to mitigate potential evasion tactics by network scanners. So in the best case scenario, the attacker can scan for a maximum of 300 seconds before being detected, because DNS records will expire and so require new valid DNS lookups. On the left bottom of this slide, you can see a piece of my Python script, and I will link this in the description of this video. This is the script implemented on VM3, so the scan detection system. So this Python script tracks DNS responses, alters their TTL values, and logs or block connections, identifying those without a preceding and valid DNS lookup as scanning attempts. And this is possible thanks to NetFilterQ and SCAPI libraries that I choose to use in my implementation. In fact, NetFilterQ is the module that serves as a bridge between the Linux filter framework and user space programs. In fact, it allows packets to be intercepted, modified, inspected, and reinjected back into the kernel. So by using IP tables that as you know, it is used in Linux to configure the NetFilter framework, is employed to set up rules that redirect traffic to the NetFilter queue, allowing then the Python script to process these packets. And another library that I used, as I said before, is Scapy. It is really powerful Python library that I use to manipulate packets, and it also enable the creation, modification, and analysis of network packets at various layers. In fact, I use Scapy to parse and inspect packets, extract and modify DNS records, and manage other network-related tasks, let's say, such as identifying suspicious connections and handling DNS queries and responses. As you can see on the right of the slide, this is a summary of a Scapy packet that I want to show you because I want you to focus on the TTL values modified to 300 seconds for all the DNS records of type A or type AAAA, so IPv6, for all DNS resource records, as you can see here. Not modified for CNAME because obviously is useless. So to summarize the detection algorithm, so the main features of the scan detection system, they are DNS response manipulation, because the scan detection system, as we said before, intercepts DNS responses designed for internal machines, and it modifies the TTL values of all type A and type AAAA DNS resource records to short duration, for example 60 to 300 seconds. In our experiment, for example, I choose 300 seconds. Then the scan detection system recalculates the UDP header checksum and forwards the response, the DNS response. In this way, the scan detection system ensures that machines cache only the most recent DNS records, thus preventing the use of outdated cached IP addresses for scanning. Another feature is the detection of unauthorized connections. So the scan detection system detects outbound internal scans targeting external IP addresses. It maintains a hash table, as I said before, of DNS responses and DNS queries, so DNS lookups. And thanks to this hash table, the system then verifies if the connection attempt was preceded by a valid DNS lookup within the adjusted period. Connections that lack a corresponding recent DNS query are flagged as potential scans. And another feature is local processing and scalability, because the scan detection system operates within the local subnet, so LAN or VLAN, without requiring global clock synchronization, and each of these scan detection devices are responsible for their own subnet, so enhancing obviously scalability and simplifying deployment. And the last feature is flexible response actions, as you can see in the slide, and because upon detecting a scan, the scan detection system can either drop the connection, log it for further inspection, or both, based on predefined security policies. It also allows for additional actions such as delisting or quarantining the scanning machine if required, and as I did in my script. So you can understand that the scan detection system is really helpful in an enterprise network infrastructure, since it can detect malicious internal activity, identify compromised devices, and most importantly, preventing external threats and reducing attack surface. On the left of this slide, you can see the pseudocode of the detection algorithm, while on the right, I just want to show you the possible network architecture where the scan detection devices are placed on the border of each LAN, and up there is a screenshot of a command that I will show you in a moment, executed on the scan detection system script. So this command is really useful to understand what are the current DNS records stored in the script's hash table. And as you can see, there is the source IP, this one, of the IP of the Benin client in this case. So yeah, of the Benin client, and that has completed a DNS lookup towards a destination IP address. In this case, is an IPv6 address. So let's suppose it is Google IPv6 address, and this pair, these two concatenated IPs, represents the key of the hash table, as I said to you before, as I explained to you before. And while on the right we have the value of the hash table, that is this, and with the that is the expiration time and date of this DNS record. And as you can see, if you look to the time, it is 23, 18, and 45. So this means that this DNS lookup was made exactly 5 minutes or 300 seconds ago, as the TTL that the script modifies dictates so. Okay, now let's look at the results. So once the Nmap scan started on VM2 scanner machine, the scan detection system on VM3 detected some reverse DNS queries that are done by Nmap by default to check the liveness of the targets. So upon detecting them, the VM3 script intervened and blocked them. And this is because a clever attacker might try to bypass the detection system by first performing reverse DNS queries on the target IP addresses to retrieve the domain name, and then conducting a valid DNS lookup towards the domain names corresponding to them, and these DNS records would be stored in the script's hash table. So this would allow scanning of these target addresses without detection, since valid DNS records for those destination addresses obviously would now exist in the hash table of the scan detection system. However, this is not possible because the script blocks all reverse DNS queries except for those like the Benin client that has previously performed legitimate forward DNS lookups that obviously the script has saved in its hash table. During the scan initially proceeded at normal speed, but then the latency, as you can see, increased dramatically. So during the experiment, the scan detection system proved highly effective. In fact, suspicious scans were detected and blocked after several attempts, significantly slowing down the Nmap scan run by VM2, so the scanner machine. For example, as you can see in this screenshot, the entire scan took about 5 hours, more than 5 hours to complete, and gave no significant results other than just the discovery of one single open port. The system proved so resource efficient as well. Despite the modest configuration of VM3, so the scan detection system, which uses only one CPU and 3.8 GB of RAM, the system maintained a low average CPU usage of just 8.72% and memory usage of just 32.68%, with a packet latency of just 0.00001 etc. seconds. So this is really low. Furthermore, the file containing DNS data was only 32 kilobyte. So this file is the file that saved the DNS expiration table with all the DNS records, And this demonstrates that the system can handle large values of DNS traffic with minimal impact on resources. Just only 32 kilobytes is really low. So, however, there are obviously some limitations. So, one issue is the increased load on authoritative DNS servers due to the reduced TTL values that the script modifies. Another critical point is the accuracy in distinguish between legitimate and malicious traffic, particularly for legitimate connection that do not use DNS. Obviously, a potential improvement could involve integrating machine learning algorithms to enhance accuracy and to reduce false positives. But this is not explored in this work. So now I will briefly show you in live the experiment. So this is VM1. See, this is the auto browsing script, and we can run. We first have to run the script on VM3 that, as I explained you, has two interfaces. One is bridged adapter and one is to connect with the other two machines. And let's do this. Python 3, why not .py? That py. Okay. Okay. IP tables drew added successfully. Perfect. So we can go now to VM1 and do auto browsing. So launch the auto browsing script, and okay, let's hope it works. Okay, so we have to wait a moment, and you will see it will browse. Yeah, it is browsing a list of websites, the most known websites. Okay, so now let's go on VM3 to see if, okay, all is running good, perfect. It just printed, it just prints every 10,000 packets summary of the latency of the CPU and something like this, just key performance indicators. And let's go to now to the scanner. So this is the command that I show you in my presentation, my PowerPoint, and this is the command that we will use. So let's run it. Okay, so it is running, and let's go to the VM3 scan detection system. And as you can see, my fellows, okay, so the scan detection system is blocking all reverse DNS queries and done by Nmap by default, and also has detected suspicious connection from this IP, and this is the IP of the scanned machine, obviously. Moreover, I set a threshold, and once it arrives to 100 packets, wait a moment, here it is, it blocks this IP, so the scanner machine VM2 IP. And for, I don't remember good, I think it was 10,000 seconds, something like this. So you can see here that all the connection attempts from this IP, so the scanner machine IPs, towards remote IPs, are all being blocked, all of them. And I can't show you right now that the Nmap complete all the scanning, because this scanning activity will take a lot of time, obviously, but you can see just here that the remaining time, so the estimated time to complete the wall scanning is increasing really. So let's look. 15 minutes, go to 28, then 39, and I guarantee you that it will increment a lot. So this is the script. This is what the scan detection system do, and it works good. So for now, let's just stop the scan, and I guarantee that you can prove it by yourself. I will link, as I said, the Python script in the description of this video, so it will link to my GitHub page. And so for now, let's just stop it. I guarantee that no open ports are discovered, and obviously Nmap can't perform version detection, OS detection, service detection that are used obviously for exploitation by malicious actors. But you should know this, yeah. So I want to show you one thing that is this one. So other common. This is really important because the scan detection system accepts commands that I set up, and let's do help. As you can see, this is the print hash table command that I show you in my slides, and if I do this, you can see all DNS records, so all the successfully completed DNS lookups with their expiration time. In fact, as you can see, it's 19 and 22, so the expiration is just 19 and 25. So it's 5 minutes as the TTL values dictates is 5 minutes. In 5 minutes, these DNS records will expire. Okay, so let's see the banning client. Okay, the banning client just completed the browsing. I just put just a bit of just some of the websites to browse. And let's return to the scan detection system. What I want to show you is, if we type help again, there are a lot of commands that you can use. For example, we know that the scanner IP, so machine VM2, is blocked. So we want to show that we want to print blocked IPs. So let's use this command. Okay, so print blocked IPs, and as you can see, this is the IP of VM2, sorry, so the scanner machine, and this is the expiration of this blocking. So at 1933 will be unlocked, unless you can do also like unblock IP. You can use this command, unblock IP, type enter, and enter the IP you want to unblock. So in this case, 192.168.100.4. so the scan detection system that I won't show you before this. So this is scanner, okay, yeah. If we do, for example, ping google.com, okay, it can't do anything because all the packets sent from this IP will be blocked. So if we unlock this IP, let's see. Okay, sorry. Okay, I just typed it here. I type enter. We can see unblocked IP. And in fact, if we return to the scanner machine, we can now ping google.com as we were banning client. That's it. That's pretty much it. Yes, I think I show you the experiment, just something. You can prove a lot of things. You can prove a lot of commands, also nmap commands to test this scan detection system, and based on DNS. So I think I hope you enjoyed the video. I hope you enjoyed my work, and that's it. Thank you guys for watching, and see you.